Okay, so it is good to see everybody. I hope you had yourself a good weekend. Despite the Thursday night, we had a pretty horrific storm, but I hope everybody came through that okay. All right, so let's see, what are we doing this week? So here is our website. Remember, if you're ever absent for any reason, all of the information is going to be posted here, along with links to the videos that I'm recording. In fact, Ms. Gonzalez is out this week, but well, I'm going to be using notebook files. If you want to go back, she posted slides for all the information we're going to be looking at in the next couple of days. So that is still available to you if you would like. But let's go ahead and take a look specifically at what our schedule is going to be. So there's the daily schedule. Let's see, so we're right here Monday the 9th. Okay, so we're looking at data analysis today, specifically data interpretation, measures of center, and measures of spread, which will include standard deviation. So we're going to get the opportunity to talk about that today. Before all that, we're going to look at focus activity number 6. And the only paper that you picked up today on the front table was the second homework assignment. So this one's going to be over systems. So we'll accept that through Wednesday, because on Thursday it's the last day of the June program. We won't see you folks until July. In fact, specifically when in July? The 14th. There we go. 14th, 15th, 16th, 17th. So that week we'll be back. And then I believe we have a couple of Saturdays in the fall after that, but we'll let you know what those dates are the closer we get. So tomorrow we're going to be talking about data analysis as well. Now, the homework, like I said, you can go ahead and turn this in through Wednesday, because we're going to do the raffle on Thursday. So we're not looking for accuracy. I mean, we would like accuracy, but as long as you complete the homework assignment, that gets your name in the drawing for one of the gift cards. And then after we talk about that tomorrow, we got a quiz over systems. It's going to be formatted, look like the same type of problems you have on your homework. Okay, and then you can see for the rest of the week, we got a couple more focus activities. We're going to be focusing on a strategy called Easy McSqueezy. It's a ridiculous name, but it actually is a really good strategy for a lot of students. We'll talk about that on Wednesday. And then Thursday, after our final focus activity for this month, we're going to go ahead and end up with another game where we can use it as a kind of a review. Okay, so any questions about what's coming up this week? Okay, well, let me go ahead and get rid of this. All right. Focus activity number 6. Let's go ahead and get to it. First off, does anybody need a copy of this? Okay. I got plenty of copies in case anybody misplaced one. There you go, sir. Okay. Anyone? Okay. Anybody else? Fantastic. Okay, well, let's take a look. Starting with number 7. Now, we've actually seen several of these types of problems over the past couple of weeks. It says, okay, let the function h be defined by h of x equals 14 plus x squared over 4. And if h of 2m is equal to 9m, what is one possible value of m? So they're giving me a function, and just like we've seen multiple times before, we've got a blueprint for how to create the equation. Okay, so how would I figure out h of 2m? Yeah, just plugging it in. Whatever's in parentheses is the element in your domain. So I'm going to start with the 14. Then we're going to have plus. So x squared becomes this product 2m squared over 4. So there's the left side of your equation. And then it equals 9m, so there's no reference to function h. It just equals this product. So I'm going to say it equals 9m. Okay, so let's work through this. The product 2m squared would be 4m squared, in which case these 4's are going to cancel, and we're ending up with a quadratic equation. So let's go ahead and get everything to one side. Oh, did I make a mistake? Oh, then we have m squared. If I subtract that 9m over, plus 14 is equal to 0. And a week ago, we talked about a lot of strategies for solving a quadratic. Among them, quadratic formula, completing the square, which are all perfect strategies to use. I would probably just factor. What two numbers will multiply to give me 14, but add to give me -9? -2 and -7. So m minus 2, bless you, times m minus 7 equals 0. But what do I do with those groups? How does that help me find my answers?
You equate them to 0.
Equate them to 0. Zero product property. So if m minus 2 equals 0, well then my first solution is 2. If m minus 7 is equal to 0, well then we have m equals 7. And it did say what is one possible value. So it is, odds are good that you could end up with a question where you have multiple answers, but on the real PSAT, you would only have to choose one of them, and you are good to go. Okay, questions?
Are there any? So in a lot of these problems, some answers will not equate, or they won't factor, right? If you put them in.
Yes.
So
So some of those won't factor.
would you recommend checking like every question? Or?
I would always probably start with factoring because I think it's the fastest, most efficient method. But only then, if factoring doesn't work, will I go ahead and turn my attention to, say, quadratic formula.
No, I mean like after you get your two answers.
Should we plug them back in? You can. Would you like me to plug it in and see that it works?
No, I'm just asking if you would recommend it for every question. That'd be
Probably not. I mean, now, if you're dealing with something like maybe a rational equation, maybe a radical equation, things like those, because there could be extraneous solutions, I might go ahead and do that.
so,
But with a quadratic, I don't think that's going to be necessary.
so just with rational and straight. Okay.
Yeah, those that could have extraneous solutions. Yeah. Okay. Cool. All right. Moving on. Okay. Then we got number 8. It says, we got a little bit right there. Luke purchased an automobile for $5,000 and the value of the automobile decreased by 20% each year. The value in dollars of the automobile in years from the date of purchase is given by the function v, where v of n equals 5,000 times 4/5 to the n power. How many years from the date of purchase will the value of the automobile be 3,200? Now, we are going to go ahead and solve this equation, but one thing I'd like to point out, they've already given you what you need. You could test the test. And I went ahead and brought that up for the first time last week. That means using the answers to find which one is correct. So you could plug all of these in and see which one gives you the 3,200. That would be one way to do it. But like I said, we're going to do it the algebra way. So 3,200 is equal to 5,000 times 4/5 to the n. So we're trying to solve for n, so the first thing I do is get rid of that scale factor. So let's go ahead and divide through by 5,000. Those are going to cancel. Now, with values such as this, I can cancel out groups of zeros. So 4/5 to the n, what is 32/50ths? I'm sorry.
32/50th?
Yes. What would that simplify to?
16/25.
16/25. Okay. Now, solving this algebraically, there's several routes you could go here. My first idea would be to go ahead and just take a log. Because you're looking for a power, you could easily rewrite this and go ahead and figure out what the answer is. But let's say maybe you're not wanting to go that route. Maybe you are, because logs are super fun. You could also do this. Do you notice any comparison between what we have 16/25 and the base over there, 4/5? What's that? 5. Okay, there we go. So 25 is 5 times 5, right? So what if I rewrote it like this? What if I said 25 is 5 squared and I said 16 is 4 squared? And that's equal to 4/5 to the n. Well, if I've got the same power on both of my bases here, couldn't I just say that's 4/5 quantity squared equals 4/5 to the n? And remember, this is one of your exponent rules. If one exponential equals a second and they have the same base, their powers are the same. So I know that n has to be what? 2. What's that? Oh, that's the other question. Okay. Questions. Easy, right? Did anybody solve it as a log? No? Hopefully logs aren't going to stump anybody. Log, stump. You know what? There's a connection there. I will go with that joke. Okay. Are you ready to log on? That one's good too. Yeah, they're all good. Yeah, okay. All right, numbers 9 and 10 are given with functions g and h. Okay, so number 9 is pretty straightforward. It's just function notation. So let's see here. We want to find the difference of g of 5 and h of 4. Well, let's see, g of 5. So that would be n squared plus n, so that's a 5 squared plus 5, and that would give me 30. And now let's calculate h of 4. So that would be 4 squared minus 4. What am I looking at there? 12. Okay, so since I stacked them like this, just subtract them, what's the answer? It's got to be 18. Okay, now for number 10, which of the following is equivalent to h of m plus 1? So if I go ahead and plug m plus 1 into this second function right here, which of these answers would give me a similar expression? Okay, so let me give you a minute to take a look at that, and then we'll talk about it. Think you got it? You want me to check your answer? Okay. Yes. So you take whatever you have for the function, and whatever expression you get, you would just put a plus or a minus 1 at the end.
Okay, got it. So it's just
Different. Because in this case, the plus 1 makes it a binomial, so you have to expand that when you're looking at the function. Oh, yeah, to convert to a log. Yeah, because there's always 3 parts to a log. You've got the base, the power, and the argument. And that's all a logarithm is just a power. So in this case right here, if we've got, give me 1 second. So if we've got like 16, 25ths equals 4/5 to the n. So you can identify the base and the power very easily, so that's got to be the argument. So I would say log base 4/5 of 16 25ths is equal to. And then when you're putting it in, if you're using Desmos, you can actually either just type log or look under functions. And if you're using it on the Inspire, okay, if you go ahead and hit, what I like about this, if we go ahead and hit A, if you hit Control and then 10 to the X, see it provides you a space for the base and the argument. Yeah.
Where did you get the? I know it has it here, but like, why are you dividing?
Oh, because my goal is to isolate that variable.
Oh,
So I want to go ahead and slowly remove anything that's associated with it.
okay. Where did you keep? Where this G came? Cause like, I don't get how does like.
Okay, so let's look at this. Okay. Okay, so which of the following is equivalent to h of m plus 1? Well, the first thing we need to do is figure out what is h of m plus 1 going to look like. Okay, so remember, h of n, that's just n squared minus n. So h of m plus 1 is going to equal n squared, so m plus 1 quantity squared minus n, so minus m plus 1. Again, the fact that it's a binomial changes nothing. Now we want to go ahead and expand this. Now you could definitely use FOIL, first outside, inside, last. But remember, there was also a clever little rhyme we talked about last week. Square the, what that L stand for? Left. Okay. So if I square the left, I get m squared. Square the right, so 1 squared is 1. Now double the middle. Remember, that means to multiply the two terms together, so m times 1, and then we double that. So plus 2m. And then here, all we're doing is just distributing the negative, so minus m minus 1. Well, immediately we notice that the 1's cancel. So it looks like we're going to have m squared plus m. So this is my target expression. That's what I want. That's h of m plus 1. So if I were to go ahead and take a look at some of these answers here, which one would simplify and give me the exact same thing? Anybody think they figured it out? It's got to be A. Okay. Because take a look. G of n is just n squared plus n. So if I were to go ahead and replace n with m, well, then we already have m squared plus m, which is exactly what we want. Okay. Now, ma'am, would you like me to go ahead and plug into one of the other answers just quickly? Do you have one in mind? Okay, let's just try B. So let's say that we think that B might be the answer. Okay. Remember, G of n is n squared plus n. So let's test G of m plus 1. Okay. So only this portion is going to deal with function g. So G of m would be m squared plus m, and then we want to tack on this little plus 1 at the end. So it has the two terms, but it also has something additional that we don't need. So that's why B is not the right answer. Okay. Now, this is the way you do it algebraically. The only other way I could think to work a problem like this was if you went ahead and chose a value for m. Okay, whatever you want it to be, like we've seen that on several problems before, go ahead and plug that in, get yourself the value, and then just plug it into the answers and see which ones come out with the same one. Okay. All right. How many people got all 4 of those correct on the focus activity? Nice. What about 3? Nice, nice, nice. Okay. Were there any questions? Okay. Well, then we're going to go ahead and put the focus activity to the side. Save changes on that. And here we go. Okay, so before we go ahead and get started with the Sarago material, again, I do want to show you this. So for today, the 9th, this is what we're doing, data interpretation, measures of center and spread. But tomorrow, these are the concepts that we're going to go ahead and try to cover. And I say try because, remember, we're going to have a shorter class tomorrow because of the homework and then because of the quiz. Okay, so please, 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 that's what makes it so important. These two concepts here that I have highlighted, sampling and inference and sample bias. Each one starts out with a couple of pages of description. They start talking about it. Please take a little bit of time. It takes like 5 minutes. Okay, read through those. So you're going to have a better understanding of what we're talking about when we get into it tomorrow. It's page 209 and page 213. And there's a lot of advantages to the Sarago binder. Before any topic, it does discuss that topic. It gives you several examples, talks about how to work through them. And what's even better, our time here is limited, so there is no way that we can absolutely do every single problem in every section. So you're going to have more problems in the resource to look at beyond what we do in the classroom. Now, that's to say that when you go home and people are wanting to do math, right? Because you go home and you're like, I don't want to hang out with my friends. I want to do some statistics, right? I'm sure those are normal conversations. But if you are looking at any of these concepts and you come across a problem that you're not understanding, let me know. Go ahead and come on in during Q&A, or if maybe it's sometime during the summer, shoot me an email, shoot Ms. Gonzalez an email. We'll definitely help you out. Now, there is one disadvantage to the Sarago binder. Once you get to the practice sessions, okay, they're great, but while they have the answers at the end of each section, they don't provide elaboration. So they give you the answer, but they don't give you any way or indication of how they came to that answer. So that can be a little confusing sometimes. But let's go ahead and get into it. Okay. So if you'll go ahead and turn in your Sarago binder to page 182, and specifically, we want to go a little bit further ahead because this concept of data interpretation begins on page 182, but these are the worked examples. I'm not going to go ahead and run through those because you can take a look at those at your convenience if you want to for additional examples, but the actual practice begins on page 185. Okay, so page 185. Okay, so So this is an incredibly important skill set to have. You know, if you're given any kind of visual, whether that being a bar graph, a pie graph, histogram, scatter plot, anything, that you be able to understand the information that's being displayed, but also be able to interpret it. Also be able to understand anything you can do with that information. So let me go ahead and jump to this right here. Okay. Now for this first one, I've already got it. So we're just going to go ahead and start running through problems. We'll do some together. We'll go ahead, have you try some on your own, and then we'll go ahead and talk about them. Is there anybody who doesn't have a binder? Okay. I don't know if we have any additional ones. I don't think Mr. Haskins is here today. So I'll tell you what, for today, would anybody be willing to let these two ladies kind of look on the paper with them? Yeah? Okay. So we got Evan here who's going to help out. And Nathan, you got yours. Would you be willing to? Oh, you have yours? Oh, okay. Then I didn't see it. It was behind you. Okay. Okay, then we're good. We're good. Okay. All right. Let's go ahead and get through this, because not only do I want to practice this, but I want to make sure we have enough time to get through measures of spread before we leave today. Okay, number one. Given the circle graph below, which of the following statements is not true? So that means that when you read through this, I would absolutely encourage you to read through all of your answers. 3 of these will be true, 1 is not. So to make things a little easier, because I'm a very visual person, I went ahead and labeled the sectors on my circle here. Like, it looks like chocolate takes up the majority, followed by vanilla, strawberry, banana, cookies, and cream. And I'm actually kind of surprised about the size of the sector for banana, because I thought way more people would find that appealing. Thank you, thank you. Well, I haven't gotten far enough yet where I need to split, so. There we go, right. Okay. All right, well, let's see. So, A, let's just go right down the choices here. So, more people prefer vanilla than banana. Is that true or false? Well, it looks like vanilla's sector is larger than bananas, so that's true. Now, remember, we're looking for the one that's not true. Okay. Okay, chocolate was the most preferred flavor. Is that true? That's true. Together, chocolate and vanilla were the favorite of over half of the people. I'd say that looks almost 3/4 to me, yeah. So right here, by process of elimination, it has to be D before we even read it. Banana is a more popular flavor than strawberry. No, strawberry sector right here is larger than banana, so that's the false statement. Okay. There we go. Okay, moving on. Number 2. Sam rode his bicycle from school heading toward home. He rode quickly at first and then slowed down, but he did not stop until he reached home. Which graph best represents the situation if the vertical axis represents the distance from school? Okay, so on this one, let me give you about a minute to think about this. Okay? And then we'll go ahead and discuss it. And remember, you could go ahead and approach it from the perspective that you would create the graph yourself, or you can go ahead and look through and try to find maybe a characteristic or something that would eliminate that graph. Anything you can do to eliminate answers is a great strategy. Seconds. Okay. Let's see here. Colin, what you got? It is D. Okay. Now, here's the thing. He is going home, but the graph is tracking the distance from what? So the further he gets from school, the distance is increasing. So it has to rise to the right. I mean, that already eliminates A and B. Okay. And in fact, B was already eliminated because what? He rode quickly at first, but then he did what? he slowed down. His speed wasn't constant, so it's not linear. That also eliminates C. Okay, very good. Okay, questions 3 and 4 refer to our given graph here. Number 3, the graph at the right describes the average growth per month measured in centimeters of children of various ages from 1 to 2 years of age. According to the graph, which of the following is the best estimate in centimeters of the growth of a 20-month-old child? Okay. So let's see. Zoe, can you help me out with this one? So we're interested in a child that's how old? Okay, 20. So what would be the corresponding height or length, I should say, of the child? So here's the 20 that we're interested in right here. So I'm going to go straight up. I'm just going to go straight over here. So what answer is best going to represent that? 1.6. Okay, it's definitely between 1 and 2, so it can't be A or B. And it is, for me, not nowhere near close enough to be the 1.9. Okay. Good, good, good. Okay, number 4. What is the approximate average rate of change in the growth of a child from 12 months to 18 months of age in centimeters per month? Okay, well, there's a critically important phrase here. When it says average rate of change, what are we talking about?
The amount changed.
The amount changed? I'm looking for some algebra term starts with S. Slope. We're talking about slope. Okay, so our slope is always the change in y over the change in x. So you might remember it, y2 minus y1 over x2 minus x1. Okay. So let's go ahead and take a look at those points in particular. Okay, so we're interested in the average rate of change from 12 to 18. So when we have a 12-month-old, according to this, they're 2 centimeters long. So I'm going to go ahead and say 12. 2. So now for the next one, we're going to have to estimate because we're interested in 18 months old. Now, I went ahead and put 2.8. Okay. Whoop. Let me go ahead and get that correct on there. So I said this was 18 and 2.8. Okay. And, maybe someone's going to say 2.9, maybe a little bit higher, lower than whatever I did. So I just estimated it. So let's see. 2.8 minus 2 divided by 18 minus 12. Okay. So 2.8 minus 2, looking at a 0.8 over a 6. So you can double check on this. I got about a 0.13. Now, what you have to realize that there's often going to be problems where you're not going to be finding the exact answer because part of your calculation is going to be based on an estimation. So you want to choose the answer that's closest to what your value is. So in this case, what would it be? Okay. 1.5 is closest to what I found. Okay. 2.9 would work as well, yeah. Is that what you use, Colin? You use 2.9 for 18? Oh, gotcha. Okay. Does that make sense, though? Now, all we know is that we're just using information provided in the graph here. What?
I thought the numbers were like how many centimeters like per month that it was growing.
Well, basically, we're doing it over multiple months. So basically, if I were to connect these 2 points, we're trying to find the rate of change of that line right there. Now, that's the average.
How much it's growing.
Yeah.
Okay, so we're not actually talking about how much it's growing, but how the rate of change of it growing is changing.
Yes. So with respect to the 2 quantities we have here, that's the thing. Is everybody okay with that? Okay. Ooh, on that one, we were kind of on a slippery slope, but hey, it worked out. Hey. Thank you. All right, let's try number 5. According to the graph below, approximately how many more households had 2 or more cars in '04 than in '02? Assume that the number of households in the county has remained relatively stable with 110,000 for the years '02 to '05. Okay, so you folks help me with this one. How would I approach this problem? Yeah. So when it says how many more households, what operation is that telling me to use? So we're going to subtract. We got to find the difference. Now we're only interested in '04 and '02. Okay, so '02 and '04. So all this graph is providing me is the percentage of households within that year that had 2 or more vehicles. Okay, so why don't we go ahead and start by identifying what we think the percentages are. What's the percentage you think for '02? Let's say 47%. Yes, I was going to go ahead and say that. This one here in '04, it is slightly above. It's definitely nowhere near enough to be 51%. That's exactly right. Even though it's a touch over, I would still go ahead and just say that's at 50%. So I know that there's going to be a little bit of discrepancy in what I'm looking at here. But we're going to take these percentages of what number? The 110,000. Okay, so I'm going to convert these to decimals. So 0.5 of the 110,000. Well, that one's easy. We don't need a calculator for that. That's 50. Half of 110,000?
Oh, you're doing 55,000?
55,000. Okay. And then I want to take 47%, so 0.47 of the 110,000. Somebody help me out with that, would you? So I got 51,700. So that gave me a difference of 3,300. Again, we knew it wasn't going to be perfect, but what answer is closest to what we got? B. 3,500 households. Okay. Not too bad, right? Okay. Well, moving on. Okay, so number 6 through 8 are going to fall within this graph right here. Okay, so we'll do the first one together. It says the city of Round Grove has a $1.2 million budget for its Parks and Rec department, which was a great show, by the way, if you never watched it. Ron Swanson. As displayed in the chart, if the parks and facilities maintenance categories are combined, what fraction of the budget is not spent on maintenance? Okay, so help me out. How would I do this? Remember, we want those aspects of the budget that are not spent on maintenance. So would that include parks maintenance?
Yeah.
So I'm not going to include that. And I'm not going to include facilities maintenance. But I do want athletics programs and advertising. So how much of the budget is spent on athletics? 400,000. On advertising, it looks like 100,000. So together, that is 500,000 of the budget, which is 1.2 million. Yeah, so I'm taking a ratio. So I'm going to go ahead and start dividing off the pairs. So looks like we end up with 5/12. Okay. All right. And now what I want you to go ahead and do, take a minute, answer numbers 7 and 8 using this bar graph. Okay. Yeah, so right now we're only working 7 and 8. Seconds. You're doing both 7 and 8, yes. All right, let's take a look at 7. Which of the following ratios of different departments' budgets is closest to the ratio of the budget of parks maintenance to athletic programs? So can anybody tell me out, what should the ratio from parks maintenance to athletic programs be?
1/2.
Should be 1/2. Okay, so I'm looking for 2 of those that'll give me the same ratio. Who found it? It is C. Okay, advertising to parks maintenance. Okay, advertising 100,000, parks maintenance 200,000. There's your 1/2. If you wanted to know the rest of them, I went ahead and figured them out. A had a ratio of 4/5. Okay, then B had a ratio of 2/5, and finally D had a ratio of 1/5. Okay, just in case anybody was interested. Okay, and number 8, based on the bar graph in number 6, which of the following best displays the breakdown of Round Grove's $1.2 million budget as shown in the charts below? Okay, there you go. What I would do for this one is go ahead and start with the largest and the smallest aspects of the budget, and then start to look at which the circle graphs has that. In fact, the largest was facilities maintenance. Oh, you start with the smallest?
I figure we should start getting rid of one that only has 3.
Oh, no, yes, sir. Yeah, that's another good point. And then advertising here, I believe that was the smallest.
Or the one that has 5 and the one that has perfect order.
Okay,
I feel like it's just like this. It's just eliminated.
there we go. So it has to be D. Okay. And I mean, honestly, like you said, you can go ahead and get half of the answers gone already because A, like you said, it only has 3, not 4 parts. Oh, I know. But these are probably the easiest because this one says that all 4 of them are going to share an equal amount of the money, and that's not true. Okay. So good. How many people got both those right? Fantastic. I know, right? That's a well-run city right there. Fine. Okay, number 10. Based on the histogram below, which is closest to the average? Oh, sorry. Actually, let's skip number 9. Flat tire repairs. I did. Okay, so number 9. We'll get to that other one in a second. The number of flat tire repairs over a 5-month period is shown in the chart above. If the total number of repairs is 2,550, what's an appropriate label for the vertical axis of the graph? Should it be the number of repairs in ones, tens, hundreds, or thousands? Harrison, what you got? It should be in hundreds. Okay, so somebody help me out. How can we determine that? Okay, exactly. So you're just kind of reasoning your way through? Look at it this way. Let's just go ahead and individually count up what each bar has. Like January, let's just say it has 6, right? So then February is 3, March is 4, April is 5. What would you say for May? Okay, so 7.5, bless you. Now, somebody go ahead and add up all of those numbers for me real quick. 25.5. But we're told that there were 2,550, so we'd have to move that decimal 2 places over, and the only way to do that is by hundreds. Okay. All right. Good. So hopefully no one's tired after that problem. Number 10. Based on the histogram below, which is closest to the average arithmetic mean number of RBIs per player? So who is a baseball fan in here? Okay, what does RBI stand for? Say again? Okay, well, runs batted in. So, yeah. Okay. All right. So, what would I do here?
You add up the values of all of them and then divide by the number of values that there are.
There you go, because they're telling you exactly what to do here. The number of RBIs per player. So, looks like I've got 4, 3, 1, 1. That gives me a total of 9.
Isn't 4, also, I guess so you should, that's weird though.
Well, there is nothing for 4.
Yeah, but like, see something, like, don't put this in that because it's included in the data system. I would argue that they put that there, that means that there's 0 for any 4.
So it would still be a member of the set.
I mean, so it's 0, but like so you would divide by an extra 1, which you're not.
I'd have to think about that. Because if we included it, then that means we'd have to divide by 10, right? Because we're including it in the set of elements. But then that would give me, that would give me 0.9.
It's just because of the way they left the.
You know, I think that would still work out. Yeah, because you're going to get closest to 1. Yeah.
Let's say which is closest. Yeah.
So you know what? I think you are correct about that.
I would just figure that you would divide by 10 there.
Yeah. Okay. I mean, is everybody okay with why he's thinking we need to divide by 10? Because they do include the 4 in the graphic. So we could go ahead and include 0. Okay. And I mean, even if we did say 9/10, it's going to end up as 0.9. So you're still going to be able to figure out what answer is correct. So I think he is correct about that. Ooh, and that thing too, I mean, 9/10, it almost got 2/10 in here. Ooh. 2/10. 2/10. Oh. Let's move on. Okay. Here we go. Okay, now this set here, I've got kind of a love-hate relationship with these problems right here. We're going to go ahead and skip those. But it does contain a couple of good problems. My issue here is that the vertical alignment of these values is off slightly. So the graphs aren't necessarily correct. So that's why I always have kind of an issue with these. So I'm just going to go ahead. If anybody's interested, for Q&A coming in, we can definitely talk about them. But we're going to go ahead and move on to the last set of questions. Okay, so 15 through 20 are going to be based on this information. Laura leaves her friend's house and starts driving towards her house. She slows down for a school zone. While waiting at the traffic light at the edge of the school zone, Laura realizes she left her cell phone charging at her friend's house. OMG. No. Okay. When the light turns green, she turns around, drives slowly through the school zone, and then drives quickly back to her friend's house to get her cell phone. She has a short conversation. Wow, that was loud. She has a short conversation with her friend and calls her mom to say she'll be a little later than expected. After she hangs up, she drives home safely at a constant speed since the school zone is no longer active. Okay, so I'm going to go ahead and give you 5 minutes to run through 15 through 20. And then I'll go around the classroom and I'll pick on different people to go ahead and give me an answer. Here we go. Yes.
It's in our house that's here.
This one, we'll see. This is where she enters the school zone. So this is indicating that she's slowing down. And then she's waiting. Does that make sense?
Yeah. Okay. Just as she's at the edge of the school zone. There. So that's the end of the school zone.
Well, no. This is the number of miles, yeah. So remember, this right here is distance. So this is time. Yeah. So when she enters the school zone, it doesn't matter like how big the school zone is, because we're not looking at it in terms of that distance. It's distance from her house. That's a good question. Hey.
Isn't the school zone like right here?
Well, no, that's where she's already in the school zone. See, she's driving, but what would suddenly make her stop driving as fast? The fact that she enters the school zone.
Because the part where she's at the school zone is between 2 and 3 miles, so do we round that or 3 miles?
Actually, you don't have to round up in this case.
But it says between. But I don't think actually that's like. I think the school zone starts. It starts at 3 miles.
There you go. So she's in the school zone for a certain amount of time. Because remember, the whole graph has only got 2 quantities. We got time in minutes and the distance from what?
Laura's house.
From Laura's house. Okay.
Speed is distance divided by time in this, right?
Or sorry,
Yes.
I'm on 19. Sorry.
Yes. Now, on
So
19,
I
you're
need to
going to...
multiply by 60 though, right?
Yes. Okay. Because your graph here's in minutes and they're in hours.
Yeah, so it's
Yes.
Since she's in the school going from there to there, it's going to be 2 minutes, right? Sorry, just making sure. Her speed is right.
Yes.
Right for run, so
Yes.
it's 2. Okay, good. So it's 2 divided by 60.
Okay, we're a little off on that.
Sorry, times 60.
Okay. So then you're also going to have a decimal value in the numerator, though.
Decimal value in the numerator? Because it's going to be 0.5, yeah?
Yes, yes, yes. So basically
I mean,
0.5 divided by 2.
I meant like for the minutes, it's 2 divided by 60. For the...
No, then you would multiply by 60.
Multiply by 60.
Yeah, so you had it right the first time.
20 divided by...
Okay. What's up?
Oh, it says for which interval is lowest distance strictly increasing? Like, it stuff like I'm assuming it wants distance from her, like.
Or it's over any of the time here, as long as it fits what it's describing. Because see, I'm assuming you're talking about this last one here.
Yes.
Now, it does give you specific intervals that you could look at and see which one fits that description.
It's just.
How fast is the word?
Like technically strictly increasing. Technically
What are we doing?
yeah, but we so this she does so how fast she's so I don't know like why 30 miles. Half a mile. And if you think about that, it's really weird that
Going a mile in 2 minutes is 30. Going 2 minutes. Half mile.
Okay, that is 5 minutes. Let's go ahead and talk about it. Okay, number 15. How far is Laura's house from the school zone? Okay, I heard 2. It is 3. Okay, because remember, look at the graph. Where does Laura start? See, this whole graph is based on the distance from Laura's house. So she starts 5 miles from her house at her friend's house. You know, the BFF? Okay. Everybody okay with that? So at 2 minutes after driving away from her friend's house, that is the first time she enters the school zone, so 3 miles away. Okay.
Did I see 2? You said 2. Oh, we put 3.
Oh, so you put 3, but you said 2. There you go. Okay. Number 16. How long did the conversation with her friend and the phone call to her mom take? That was 5 minutes. Okay. Now, as we go through these, if you're not sure why we chose a particular answer, definitely let me know. Let's go back to the graph and see why. Okay, now number 17. Between which times was Laura driving the fastest? Okay, C, between 7 and 8 minutes. Okay, now visually I can tell that's got to be the fastest speed because that line segment is the what? It is the steepest. The steeper the line, the faster she's traveling. Yes. Okay. Good, good, good. And all the way conversely to a horizontal line where time is still passing, but she is not moving at all. Okay. Good, good, good. Well, how far is the friend's house from the school zone? That's 2 miles. Okay. That's 2 miles. Okay. This is one that typically people always have a little bit of fun with. Okay. Approximately, how fast was Laura driving in the school zone? In a school zone? I mean, you can, but that is not correct, sir.
15.
Okay, it is 15. Okay, so here's what I did. Like, for example, she's in the school zone here, so she's driving here. She's driving here. That little horizontal segment, that's where she's waiting. So let's just go ahead and take a couple of endpoints here. Like this one here would be 5, 2.5. And this point right here would be 7, 3. Okay. All right. So let's go ahead and figure out what the slope here is going to be. So that would be 3 minus 2.5 over 7 minus 5. So we're going to get 0.5 over 2. So this right here is 1/4, but it's miles per what? Miles per minute. But you notice all of your answers, they're in miles per hour. So we have to go ahead and change that. So I'm going to multiply this by 60 minutes in 1 hour. Because see, I want my minutes to cancel out. Now it's in miles per hour, but 1/4 of 60, there's your 15. There we go. Well, I mean, you can drive through a school zone at 30 miles an hour. I mean, you're gonna see little toddlers, like diving out of the way, but yeah, it's not legal. You don't want to do that. There you go. Okay, you definitely won't be thinking in your head 200 points or anything like that. No. Not cool. Not cool. Okay, number 20. For which interval is Laura's distance strictly increasing and then remaining constant? It is D. Between 7 and 13 minutes. Okay. Strictly increasing and then remaining constant. So do you want me to show you on the graph?
7 and 13.
Yes. So let's take a, and then if I can, let me read. I can't talk right now. So the distance is strictly increasing and then remaining constant. So it's all about the distance. So if I go ahead and start right here at 7 and then we end up at 13. See, the distance is increasing and then it remains constant. Like for example, let's say I thought the answer was A, between 8 and 11 minutes. So if I go here, start at 8, and then I go to 11, well, it is remaining constant, but in this time frame, it never what? The distance from her house is never increasing. Because remember, she enters the school zone, but right here she remembers what? Oh, so you're okay? Okay. All right. Now, there's a couple of really good problems left in this section, 21 and 22. One of these is a percent increase. The other one's talking about comparing to a linear graph. You've got the answers already in your booklet. If anybody wants to talk about them, I would invite you to come on in. But with it being 10:59, I want to make sure that we talk about standard deviation before you leave. So we're going to go ahead and move on. And we're not going to do this in order. So go ahead and turn to page 206. Okay. Go ahead and turn to page 206. Measures of spread, and there's 2 of them that we're going to talk about. One of these you're already familiar with. The range is defined as the difference of the highest value and the lowest value in a set. This measure of spread tells only how far the highest and lowest values are from each other. Okay. Now, the one that's more important, the standard deviation is a measure of the consistency of the values within a set of data. Okay, the standard deviation is 0 when every value within the set of data is the same. As more variation enters the set, the standard deviation increases. Now, I'm not going to go into this in a super detail. Like, I'm not going to give you the formula or anything for that. If anybody's interested, I can definitely show you how to find standard deviation on Desmos or the calculator. Now, when it comes to the PSAT, You won't have to actually determine the value for a set standard deviation. Sometimes they will provide you the entire set, and you'll have that option. You may choose to go ahead and do that. So if anybody wants to, I can definitely show you. But let's just talk about the idea in general. Standard deviation is used in statistics as a descriptor. Okay? Basically, the larger the standard deviation, the more the elements in your set are going to vary in value. Okay, let me show you what I mean. I've got some examples down here that I posted. Let's say you have a set of numbers that are all the same, like 5, 5, 5, 5, 5. The value of those individual elements doesn't change at all. So therefore, the standard deviation of that set would be 0. Okay, so the more your elements vary in value, the higher the standard deviation. You'll notice 0, 1, 1, 2, 3, 3, 3, 4. Those are not the exact same value over and over again, so you are going to have a standard deviation. But the value of those, they're not varying by a whole lot. Those values are very close to each other. So it's going to have a lower standard deviation. Now, if I compare that to a set that has something like 7, 7, 15, 17, 21, 30, 42, the values of those elements vary a lot more than the previous set, so therefore it would have a higher standard deviation. Okay, so does that make sense? When it comes to the PSAT, you don't need to know how to calculate it. You just have to understand what it is. Okay, has anybody had previous experience with standard deviation? Okay, a few folks? Okay, cool, cool, cool. Now, with this in mind, oh, do you want me to leave that up there for a second? Harrison, I know you were copying that.
Yes.
Yeah, sure. All good to go? Okay. So let's go ahead and take a look at this real quick. Okay. So it says the shape of a graph describes how the data would appear in a histogram. A histogram is a graphical representation showing the relative frequency of values within a specified range of values. That's all the frequency is. The frequency is the number of times that a particular value and element shows up in a set of data. Okay. Again, I'm not going to read this, word for word because it's going to get boring, but here are all the different types of displays that we can have for our data. So uniform is when the histogram, all the bars are going to have the same height. Okay. Normal distribution is what we're most interested in. This is the one that's going to have the bell curve that you've probably seen before. Okay. All right. Now, this is what we like to work with. But when you're talking about data that's normally distributed, okay, this line straight down the middle, that represents the mean. But normally distributed data, this is where the mean, median, and mode, they're all going to be the same value. Or they're going to be really, really close to each other. What's really cool about this, even if data isn't normally distributed, we can force it to be normally distributed. But I'm getting a little too much into statistics. I'm just basically giving you the idea here. If it's skewed left, then this is how your distribution is going to look. Here's an example of a skewed right. Here is bimodal. Okay, and then of course we have multimodal. Okay, so you can kind of see why we refer to these different distributions the way we do. Okay, now it's worth noting that standard deviation should be used only if the data is roughly normal and there are no outliers. What's an outlier?
It's like way out there,
Yeah. So we're talking about a value that's or an element that's radically different in value from the others in the set. Okay, that's an outlier. But a good rule of thumb, should you always include or not include an outlier when you're performing some kind of analysis on your set? Include it. Definitely include it. Okay. Now, it says in a normal distribution, approximately 65% of the population lies within one standard deviation of the mean. 95% of the population is within 2 standard deviations, and 99.7% of the population is within 3 standard deviations of the mean. So what this refers to when it says the population, it's talking about your entire data set. Okay, whatever all the elements in your set are. So I'm just going to go ahead and run through this very quickly because I want you to understand what it's talking about with these percents right here. So let's say we have data that's normally distributed. Okay, so right here, that represents the mean, but it also represents the mode and the median. Remember, this is where all three of those are going to have the same value. So we want to go ahead and have our population, the value of our elements, within 3 standard deviations. So we're going to have 3 above, and then we're going to have 3 standard deviations below. Okay. So let's go ahead and say, just to go ahead and kind of give you a little more concrete basis here. Let's say that I have a mean of 10. Okay. And let's go ahead and say that I have a standard deviation. Okay. That has a value of, let's say, 2.2. So for standard deviations above the mean, what we're going to do is add that value. Okay, so what is a 10 plus 2.2? 12.2. So I would put that right there. Plus 2.2. 13.4. Plus 2.2. 16.6. So that would graphically represent 3 standard deviations above the mean. So if above I'm adding, what do you think I'm going to do below? I'm going to subtract. So what's a 10 minus 2.2? So that's a 7.8 minus 2.2. Okay, 5.6 minus 2.2. Oops. What was I? I was thinking 2.2 because of the LEM. Okay. Now, when we're talking about the percents here, within 1 standard deviation above and below, we're saying that right here, okay, that should represent 68% of all the elements in your set. Okay, yeah.
Oh, where'd you get 2.2?
Oh, I'm just making it up off the top of my head. Because we don't actually have to calculate it, so instead of running through the formula, does anybody happen to know the formula for standard deviation? I'm not even going to bother showing you that. There's no reason to. Okay, so I just made up a couple of numbers so we can kind of look at a graph. Okay, so however many numbers I have in my set, according to these values here, within 1 standard deviation, 68% of them should fall within those 2 sectors. Okay, within 2 standard deviations, so 2 below and 2 above, that should be 95% of your data. Okay, so 3 above and 3 below, that should be what? That should be the 99.7% of your data. So it should virtually be almost your entire data set. Now, the nice thing about normal distribution, let me go ahead and bring this down a little bit so I can go ahead and write that. Okay, 99.7% is that this graph is symmetrical. So if these 2 sections right here, they're going to be exactly identical to each other, but they're also meant to be 68%. Each one individually, what's half of 68? So this would be 34%. That would be 34%. And then you can continue to go ahead and break this apart as you go. So I know that this section right here should match up perfectly with this section right here. Now, all 4 of these together should be 95%. Okay, so somebody help me out. What's 95 minus 68? Ooh, little off. Okay, so now what I want to do, 27. Okay, I want to go ahead and break that apart. So this would have 13.5% of the data. This would have 13.5%. Now, if I continue to break this apart, this last little section, this would have 2.35%, and this would have 2.35%. So if I took all 6 of these and added them up, there's your 99.7%. Now, here's the thing. Will you have to do this on the PSAT? No. They'll probably just go ahead and ask you to identify graphs that might have a normal distribution or some other form. But I just wanted to make sure that everybody was okay with what these percentages mean. I mean, I am barely scratching the surface here about standard deviation. I could take up an entire week talking to you about it. Okay, but does this at least make sense? Pretty standard. Okay, so with this in mind, okay, what I want you to do, there are 4 problems. Well, 2, 3, and 4 are going to go off this graph right here, but I want you to go ahead and take a few moments, try problems 1 through 4, and then we'll come back and we'll discuss those. Okay, so I'm thinking, what do you think? 3 minutes? Is that enough time? You know what? I'll be generous. 4 minutes. So we're working problems 1 through 4. Mm-hmm. Sure.
Like, I know that this is, okay, so for skewed right, there's have to be, like, more, it's have to, like, actually look like, I mean, that's skewed right, though. This would be skewed left, so I guess there's one. So, when it says, like, approximately normal, it just means, like, it's generally in the shape?
Yes.
Okay.
So it's going to have that bell curve shape they're referring to. Yeah. So remember, if you're talking about normal distribution, so you have this bell curve right here. Okay, the mean is the very center of it, but normally distributed means the mean, median, and mode are the same value, or they are really, really close to each other.
I just don't remember which one this one is.
Ah, gotcha.
I know which one the vote is.
Yep.
So this one, should I answer off the idea that it is approximately normal?
Yes.
Okay.
Yes.
The average should be sort of figure it out.
Mhm.
I imagine that this was still
Yes.
You know what the answers for all 4 of the questions at the bottom of the page?
Mhm.
Alright.
Oh, yeah, that's what I was talking about before. See, it does give you the answers, but it provides no explanation as to why
You
this.
heard us go through it, like,
Oh, yeah. I trust you. I trust you, man.
I was talking to Mr. Schmidt earlier himself earlier. He's still like skewed normal. Really? Like only the past. Yeah, he's still fixing something because I got an Oh,
30 seconds. Okay, now before we go ahead and start talking through this, again, if anybody's curious, did anybody want me to go ahead and provide the formula? Did anybody want to see it? Okay. So sigma, that's capital lowercase sigma. It's going to be the square root. Okay. Well, that's a horrible sigma right there. That's a capital Greek letter. That's the lowercase version of it. Okay. So you probably recognize that symbol in mathematics, the capital Greek letter sigma. That's what you use for summation notation.
I don't know that was the name. I just knew this for summation.
And also it makes math sigma. So x minus mu
No way.
squared divided by n.
Have we seen this before?
That's standard deviation, where x is an element in the set, mu is the mean of the elements in the set. So this one here that looks like an elongated u, that's called mu. That's the signal mu. Now, you can also replace it. Some people go ahead and take the mean by x with a bar above it. That also refers to the mean. And then, of course, n is the number of elements in your set. Okay. Now, one other thing, because if anybody, looks at this video later on, they might be screaming at the screen, you forgot to talk about something. This is for the population. There is another version where you divide by n minus 1 if it's a sample instead of a population. But that's a whole other conversation. Okay. That's a great question. I'm not going to get into that right now. But there you go. Okay, so just in case. Number 1, in 04, the standard deviation for the math score for males was 116, and the standard deviation of the math scores for females was 110. What can be concluded about the scores for males and females? Okay, well, let's read through these one at a time. Since the standard deviation for the males was higher, the males scored better on the test. No, standard deviation is not giving me that. Since the standard deviation for the males was higher, the males left fewer questions blank. Nope. C, since the standard deviation for the females was lower, the scores for females were more spread out than the scores for the males. Okay, no. Remember, the more the value of your elements change, that's when you have a higher standard deviation. Okay, so that's exactly what it's saying in D. Because the standard deviation for the females was lower, the scores for the females were more consistent than the scores for the males. Remember, if your elements are closer in value, they're going to have a lower standard deviation. Okay, the more they're changing in value, the higher the standard deviation. Okay, good. Let's take a look at 2. 2, 3, and 4 all go to this graph right here. Okay. Oh, well, I've already got it circled there. It is approximately normal. Looks like I forgot to erase it from the last time. Does anybody have any questions about that? Hopefully I erased it on the next one. Yes.
So, between each bar, it's a discrepancy of about 50 units, right?
About 50 units. Yeah, you're talking about uniform width.
Yeah.
Yeah, all of these in the histogram are going to be of uniform width.
So it's a discrepancy. So how large does that discrepancy need to be before it's going to be skewed to one direction or the other? Like,
Ooh, it depends on the data set. I mean, see, like I said before, yeah, normally just if data is already normally distributed, then you're good to go. You don't have to do anything. But it is possible if you were to go ahead and look at your graph, the histogram representing your data, if it is something like skewed right, skewed left, bimodal, you can force your data to be universally normal. Okay. But that's a whole other thing. So they won't be asking you that on the PSAT. Oh, yeah, but you're good. Okay, yes.
How unnormal does that take?
Oh! How normal, like, how far would it have to be shifted before it's considered something else? Ooh,
Right side is slightly.
that's a good question. You know what? We've got our resident statistician next door. Let me go ask him. Can I borrow you for like 30 seconds? I've got a stats question, and I figure you're more qualified to answer it than I am. Okay. All right, so this is Mr. Reeves. I've worked with him for a very long time over at Lubbock High School. Okay. So we're going through the standard deviation section. Their question was, we decided that this was approximately normal.
Yeah.
So they're asking how at what point how far would this have to shift or change before we decided it was something else. And I didn't.
Until it became one of these.
Yes.
So in real world, it's all just a guess. It's an approximation. So in terms of being like skewed right, if this bar was just slightly higher, or if I don't know, let's say this data got this all shifted just barely,
So that maybe
and
we
this
have.
data scooted over here.
So that maybe these bars right here are taller.
Yeah.
Like
It
maybe
got
like
yeah.
like that or.
Uh-huh. And then these went away. So if these bars were gone, then it would become skewed right. But still, I would say it's all very, it would have to be significant. Because if I can't do that. I'm going to mess up your picture.
Oh, that's fine.
Because, like, if this bar was just slightly taller, then of course it's not perfectly symmetric. But you're still going to end up saying it's pretty symmetric. Like, it would have to be significant because, I don't know, the things that you do later in stats, the hypothesis tests that you do are pretty powerful, and they can handle, like, slight issues. But, it has to be, like, significant. So, like, yeah, like how we had the second growth disappear. Or even that, like, even if this was the situation right here, I would personally still say roughly symmetric.
Even if the first two bars disappeared.
Yeah, if these were gone, I would still lean towards symmetric. But, I don't know, now when we get there, now it's starting to be significant with the skew to the right. Uniform, you'd have to have these all somewhat really close to each other. Like maybe this bar was like this and like this. Because, I don't know, I think when you get to AP stats and beyond, you start to notice that nothing follows these things perfectly. But especially these two middle ones, B and C. Skewed right, it'll be very obvious if they want you to say skewed right.
Okay. All right. Does that help out?
Yeah, I know like half.
Oh, good. Good. Okay. So I think when it comes to the PSAT, I wouldn't imagine that they would go into this level of detail
No.
for some of these questions. Like I said, a standard deviation, as long as you have the general idea, you're going to be okay.
Yeah, they're not going to give you. Do you have a blank slide?
Oh, you can just kind of scooch down. Yeah, there you go.
They're not going to give you one like this. Let's see. I don't think they would do. Like, I would still say this is roughly symmetric right here. It's not symmetric. I totally know that. But I would say it's roughly symmetric, and they're not going to want you to say right skewed. What they would do is they would do this right here.
But with that, could someone make an argument that it is right skewed?
Sure.
Okay.
They'll do this too. Because they just want you to understand the concept. They're not necessarily trying to throw you a curveball. So this, they would say, they would want you to say right skewed. So they'll make it very obvious. They could do this, because this one's not bad. And that's still right skewed. But if you're flip-flopping between symmetric and skewed, I think you're overthinking it, and you just pick the closest one.
Okay.
But, I don't know, that gets difficult. Nathan could help out a lot. It's a classic.
Well, Nathan was one of my top students in pre-cal, so.
showed it.
Oh, they're asking about the difference between sample and population.
Oh, okay. Yeah. Yeah. Well, I don't know. What's your this P times 1 minus? Oh, so that's that gets into binomial distribution.
Oh, okay, that's
Yeah.
yeah. I'm just making sure you hear you recording.
Oh, did some people need to be Yeah. Oh, on the recording. Cool. Yeah, this deals with like binomial distribution.
Yeah.
And this would probably be closer to more like continuous data.
Since we have him in here, did anybody want to know the difference between sample and population, or are we good? We'll need it for the SAT. Sure. Sorry to put you on the spot like that.
Who said sure?
Here's-
Yeah. So, oops, that's a kind of crazy signal.
See, and there's the formula that I just gave you a few moments ago. N minus 1.
So there's this thing called, this is a really quick explanation. So there's this thing that you would calculate later in college, not even in AP Stats. It's actually it's a calculation of bias. It's not a description of bias. Like, yeah, we can all describe bias when we sample things. I think we'll talk about that maybe even tomorrow. But there's an actual calculation for bias, and they've figured out that when you do this right here, this n minus 1, it lowers the bias when you're doing sample standard deviation. So if you have every data value, then sure, you just do it this way, and it's not biased at all. But when you take a sample, what we're about to talk about, when you take a sample, you risk just bad luck, taking a bad sample, maybe just by chance alone. You have weird data values. This right here was a way that they figured out to limit that bias. It's just something you got to memorize. So, yeah. But yeah, this is population sample. And notice the letters change in here too. I guess that should be a capital N. But yeah.
Thank you. All right, so we didn't quite finish up with those last two problems. Remember, you have the answers in your Sirago binder. We didn't even get to measures of central tendency, so let's just run through those verbally real quick. What's the mean? The mean. So the average, where you take the sum of all your elements divided by the number of elements. What's the mode? Okay, that is the number that occurs the most often. And then the median is the middle value once you put your elements in ascending order. So there's a lot of great questions on here. I would encourage you to look at Sirago, but if you have any questions, come on in during Q&A. Thank you so much, folks. You had a great job today. I will see you tomorrow. Don't forget about the homework. Okay, if you get that turned in, you can get your name put in the drawing for a gift card, and we have our quiz tomorrow. Yes.
Okay, I'm going to be out of town for a long time.